Hello, and welcome to episode 3 of From Zero to Zeta. I'm your host, Rowan McKee. I live in the San Francisco Bay Area, and it's here, shout out to CSU East Bay, where I earned my bachelor's and master's degrees in mathematics. Spent most of my adult life teaching people of all ages and from all walks of life the beauty of mathematics. And today, I'm here to share that beauty with you. Let's dive in. In our previous episode, link there, we discussed the concept of axiomatization, the process of clearly writing down the foundational rules of mathematical systems. We explored historical examples like Euclid's Elements, where mathematics began not from theorems, but from carefully chosen definitions and assumptions, or axioms. We saw how changing just one rule, one axiom, could open the door to entirely new kinds of mathematics. For instance, when we changed Euclid's parallel postulate, we didn't just create a different geometry, we opened up an entirely new way of understanding space itself. We also examined modern implications such as the axiom of choice, which showed us that accepting certain axioms could lead to strange but logically consistent outcomes, like the famous Banach-Tarski paradox. The big takeaway? Mathematical structures depend fundamentally on the rules we choose to start with. Change a rule and you might create an entirely new universe to explore. Today we're going to look at one of the most fundamental and influential examples of such structured systems, groups. So, what is a group? Have you ever noticed how certain patterns repeat, creating rhythm and predictability in our daily lives? Think about the days of the week. After Sunday, we return to Monday, cycling predictably again and again. Or consider the hands on a clock. They continuously cycle through the same positions every day, predictable and reliable. These everyday cycles highlight a powerful concept, the idea of structure. Structures provide predictability, and mathematics gives us tools to describe exactly how these patterns work. One of the simplest yet most profound mathematical structures is what we call a group. Believe it or not, you've already encountered groups in this series. Recall episode 1 when we tackled the sliding tile puzzle. We saw that certain rules and patterns emerge naturally. These patterns correspond exactly to the four fundamental ideas, or axioms, that define a group. First, we have closure. Every move we made on the puzzle board led to another valid puzzle state. We never left that well-defined universe. Similarly, consider counting whole numbers. When you add two whole numbers, the result is always another whole number. 5 plus 4 equals 9. You never end up outside of this set of numbers. That's closure. Next, there's associativity. Remember the composability condition from episode 1. We learned that combining moves didn't depend on how we grouped them. Doing move A, then move B, then move C gave us the same result regardless of grouping. A, then B, then C, or A, then B, then C. Think of associativity like depositing money into your account. If you start with $20, deposit 30, then deposit another 10, the final balance won't depend on how you group these transactions. It will always be 60. The third axiom is the identity element, or simply doing nothing. In episode 1, we saw this clearly. Choosing not to move any tiles left the puzzle completely unchanged. Another example. Rotating a wheel exactly 360 degrees lands you precisely where you started. This action changes nothing, so it's our identity element in action. Finally, we have inverses. Every move we made on our puzzle could be undone step by step, returning us precisely to the starting state. Similarly, in daily life, stepping forward and immediately stepping backward brings you back to your original spot, perfectly undoing the initial action. These four ideas, closure, associativity, identity, and inverses, form the backbone of a group. Together, they create an incredibly powerful structure that helps mathematicians understand symmetry and patterns found everywhere around us. But here's an intriguing question. Thinking back to our last episode, do we invent the rules or discover them? What do you think? Did mathematicians discover groups hidden within nature, or did they invent them as tools to describe patterns they observed? Hold that thought, because exploring how mathematicians historically approach this very question might surprise you. Let's dive into that story next. Groups didn't emerge out of nowhere. Their development was driven by mathematicians confronting real practical problems, especially around solving polynomial equations. Back in the 16th century, mathematicians felt pretty confident in their abilities. They had solid formulas to solve quadratic equations, like the quadratic formula. They even cracked cubic equations. This ugly thing. And quartics, sure, they found formulas for those too, but those were anything but straightforward. Easy enough, right? But fifth-degree equations, quintics, were another story. Mathematicians hit a wall. It soon dawned on mathematicians that the problem wasn't just about numbers and arithmetic. They realized equations had deeper structural properties. How solutions related and interacted was perhaps more important than the numerical methods they previously relied on. Joseph Louis Lagrange, in the late 1700s, was among the first to see this connection clearly. He suggested that the key lay in understanding permutations, how solutions could arrange themselves, and that this could help explain solvability. Then entered Évariste Galois, mathematician, revolutionary, and unfortunately terrible duelist. Gun towards the sky. 2, 3, 4, 5, 6, 7. Born in France in 1811, Galois lived a short, turbulent life marked by political rebellion and intellectual genius. Tragically, at just 20 years old, he died in a duel, just like Hamilton's son. But here's the remarkable part. On the night before his fatal duel, under immense pressure, Galois scribbled down groundbreaking insights connecting polynomial solvability directly to symmetry groups. These notes, largely unappreciated during his lifetime, eventually formed the foundation of what we now call Galois theory, revealing that equations' solvability depended on underlying symmetries and structural patterns. Initially overlooked, classic move in mathematics, Galois' genius was finally recognized decades later. So, circling back to our last episode, do we invent the rules or discover them? Galois' story hints that perhaps the best mathematics involves a bit of both. Galois created a brilliant new way of looking at things, but in doing so he also uncovered fundamental structures that were always there, waiting patiently to be seen. With this rich historical context in mind, let's see some concrete examples of groups and understand exactly why mathematicians care so deeply about them. First example, integers under addition. Let's start simple. Consider the set of integers, the numbers -3, -2, -1, 0, 1, 2, 3, and so on in both directions. Under addition. This is one of the most intuitive examples of a group. First we have closure. Adding two integers always gives another integer. For example, 5 plus -3 equals 2, another integer. And associativity, the order in which we group addition doesn't matter. 3 plus 4 plus 5 is the same as 3 plus 4 plus 5. And our identity element, the number 0, is special because adding it to any integer leaves that integer unchanged. 7 plus 0 equals 7, and the same with every other number, including 0. And we have inverses. For every integer, there's an opposite integer. Adding them brings us back to 0, the additive identity. For example, the inverse of 5 is -5, since 5 plus -5 is 0. Mathematicians call this specific type of group an abelian group, named after Niels Henrik Abel, who studied these groups extensively. Because the order of addition doesn't matter. We'll be taking a closer look at them a bit later. Example 2. Now, let's move from numbers to geometry. Consider an equilateral triangle. 3 equal sides, 3 equal angles. This triangle has symmetries, actions like rotations, reflections, that leave it looking unchanged. First, we have closure, combining any two symmetry moves, like rotating by 120 degrees, then reflecting, you get another symmetry of the triangle. And associativity, just as before, grouping these symmetry moves differently doesn't affect the outcome. Rotate, then reflect, and then rotate again. Doesn't matter how we group these moves, the triangle ends up in the same orientation. The identity move here is doing nothing at all, simply leaving the triangle as is. This may sound familiar from the sliding tile puzzle, where our identity was doing nothing to change nothing. Inverses. Every symmetry action can be reversed. Rotate the triangle 120 degrees, and you can rotate it back by negative 120 degrees to its original position. Reflect it once, reflect it again, and you're back to where you started. Geometric groups like these are fundamental in understanding symmetries in physics and chemistry, such as the shapes of molecules and crystal structures. Now, finally, let's examine permutation groups. Permutation simply means rearranging items into different orders. We'll actually be taking a closer look at these a little bit later on. Consider three numbered balls, 1, 2, and 3. How many ways can we arrange them? Turns out there are exactly 6 possible arrangements. So, if you rearrange the balls, then rearrange again, you always end up with one of these 6 arrangements. You never leave this small universe of possibilities. And associativity, again, rearranging balls multiple times, doesn't depend on how you group those arrangements. The final arrangement always stays consistent. The identity permutation here is straightforward. Do nothing. Leave the balls in the original order. No arrangement required. Inverses. Every permutation has an inverse arrangement that returns you to the original order. If swapping balls 1 and 2 changes their positions, just swap them back, and you're back to where you started. Permutation groups are hugely important. They underpin fields ranging from solving puzzles, like Rubik's Cubes, to cryptography, science of encoding and decoding secret messages. These examples, integers, geometric symmetries, and permutations, show that groups aren't abstract curiosity. Instead, they're a universal language describing structure and symmetry across mathematics and the world around us. Next, we'll dive even deeper and explore why understanding these structures matters, far beyond math itself. We've talked about several examples of groups, but now it's time to settle into one that we'll treat as a standard model going forward, a reliable example we can revisit again and again. That model is modular arithmetic. You've probably used modular arithmetic before, whether you knew that was what it was or not. Let's say it's 5 p.m. or 1700 hours, and someone asks what time it will be in 10 hours. If you're using military time, you'd compute 17 plus 10 equals 27, and then wrap around to 3 the next day. That's arithmetic modular 24. Now, if you're using a 12-hour clock and you start at 5 p.m., someone asks what time it will be in 10 hours, you do 5 plus 10 equals 15, mod 12, that's 3 a.m. That's arithmetic modular 12. So what's going on here? Definition. Modular arithmetic is a system where numbers wrap around after reaching a certain value, called the modulus. We say that two numbers are congruent modulo n if they differ by a multiple of n. In symbols, a is congruent to b mod n means that a minus b is divisible by n. Example, 17 is congruent to 2 mod 5 because 17 minus 2 equals 15, and 15 is divisible by 5. Let's now define a specific group using modular arithmetic. Addition mod 5. We'll use the set 0 to 4. We define the operation as follows. Add two numbers normally, then take the result mod 5. In other words, keep only the remainder after dividing by 5. Let's check the group axioms. First, we have closure. Any two elements from our set, added mod 5, yield another element in the set. 2 plus 3 equals 5, which equals 0. 1 plus 2 is 3, which is 3. Associativity, we're still working with ordinary addition, just followed by a wraparound. And ordinary addition is associative. 1 plus 2 plus 4 equals 1 plus 2 plus 4. And that works for any elements in addition mod 5. So the group property holds. And the identity element 0 is still the identity. Since we add 0 to anything, we get that number back. And each number has an inverse that brings you back to 0. So when we're talking about negative integers, we were saying, negative 1 is the inverse of 1 because you add them to get 0. Well, negative 1 isn't in our set, but 4 is. And if we add 1 to 4, we get 5, which is a multiple of 5. So that brings us back to 0. So in this set, 4 is the inverse of 1, and vice versa. 2 is the inverse of 3, and 0 is the inverse of 0. So let's briefly connect this back to the mod 12 clock. This also forms a group under addition modulo 12 with elements 0 to 11. If you prefer 24-hour time, you can just switch to working mod 24. Same structure, same properties, just a different modulus. It gives us a crisp, concrete example of a group that's easy to visualize, easy to work with, and full of structure. When we talk about more abstract groups later, you'll be able to ask, is this like modular arithmetic? In a number of cases, the answer will be yes, or at least close enough to give you intuition. Just keep in mind, not every group behaves like a clock, but clocks give us a great first lens through which to see the bigger picture. So far, we've been working with modular arithmetic, a beautiful, regular, circular structure, and that's no coincidence. What we've actually been looking at is a special kind of group called a cyclic group. In a cyclic group, you can start with just one element, and by repeating the group operation, you can reach every other element in the group, like turning a crank and watching the entire machine cycle through its states. So, for instance, in our example modulo 5, if we add 1 to 1, we get 2. Add 1 to 2, we get 3. Add 1 to 3, we get 4. Add 1 to 4, we get 0. And that's our entire set. So we have generated the whole set by applying the same thing over and over again. But not all groups are like that. Some have more complex internal structure. You can't generate the whole group from a single element. These are called non-cyclic groups. So next, we'll explore this distinction. What does it mean for a group to be cyclic? What does it look like when a group isn't? And why does this difference matter?
Hello, you're watching the end of part 1 of this episode. The material ended up being a lot longer than I expected, so I split it up into 2 parts. So I will see you in part 2. Meantime, don't forget to like and subscribe down below. Thank you for watching.